Assalamu alaikum. I am Dr. Sadaf Haneef, working as an assistant professor in chemistry section, Women's College, ALIGARH Muslim University. So this presentation is regarding the faculty induction program, and the topic of today's study is phase equilibrium. So as the topic suggests, it has two words, phase and equilibrium. So there is something equilibrium among the different phases of matter. So the study of equilibrium among different states of matter is known as phase equilibrium. And as we all know, matter exists in three different phases, solid, liquid and gases. So the equilibrium that is existing among these three different phases is known as phase equilibrium. And in order to study this phase equilibrium in details, we have a very important rule, and that rule is known as Gibbs phase rule. So this Gibbs phase rule, this is used for the to study the qualitative or the quantitative treatment of equilibrium among different phases. So you can see this Gibbs phase rule. This is the mathematical equation of Gibbs phase rule, that is F is equal to C minus P plus 2. So here in this particular equation, there are three different alphabets, or I can say three different terms, that is F, C and P. So this F stands for degrees of freedom, C is the number of components, and P is the number of phases present. So if I talk about phase is something, as it is written here over here in this definition, phase is something that is defined as a homogeneous and physically distinct part of a system. Like for example, if I consider mixture of gases, so mixture of gases is considered to be a one phase system, because all the gases, they are mixed together, and we cannot separate different gases without any mechanical method, and we cannot identify whether it is oxygen molecule or it is a nitrogen molecule, but it is a mixture of gases, and hence it is this, since this is a mixture of gases, so this will be considered as one phase. Now moving on to another example, like for example, if I am having a solution of two miscible liquids. Miscible liquids means those liquids which completely dissolve with one another. So if I am having a mixture of two miscible liquids, like for example, if I am having water plus ethanol, so this will be a miscible solution, and hence this will be considered as a single phase system. Now moving on to another example, like for example, if I am having a mixture of a solution of two immiscible liquids, like for example, if I am having a solution which is made up of water and oil, so that will be a two-phase system, because I can clearly see a distinct boundary, a distinct separation between oil and water. So this will be giving me an example of a two-phase system. So this is how we can explain phase. Now moving on to the components. Component is something like, for example, if I take an example of water. Water, it exists in all the three states of matter, like so it can exist as solid, that is ice, it can exist as liquid, that is simple water, and it can exist as vapor, and that is steam. So since water, it can exist in all three different phases, but overall I am talking only about water. So this water, although it can exist in three different phases, but component is only one, and that is water. For another example, if I take an aqueous solution of sodium chloride, if I take an aqueous solution of sodium chloride, that is water and sodium chloride, although it is forming a clear solution, it is forming a single phase. But here, in order to explain the state of aqueous solution of sodium chloride, I have to explain the states of water, as well as I have to explain the state of sodium chloride. So it will be a two-component system. Now moving on to the third parameter in this Gibbs phase rule, that is the degrees of freedom. Now this particular degree of freedom is defined as something by which we can explain the state of a system. And for any particular system, we are having 3 degrees of freedom, and that degrees of freedom, they are temperature, pressure and concentration. So these 3 variables, they are required for a particular system to explain the state of that system. Now again, I am going to this to the first slide. So suppose a system is F is equal to 0. According to my Gibbs phase rule, that is F is equal to C minus P plus 2. If somehow I am getting F is equal to 0, that at that particular time my system will be considered as invariant system. That is, now I don't require any variable to explain the state of the system. Suppose if I am having somehow f is equal to 1 with the Gibbs phase rule, f is equal to c minus p plus 2. If I am having f is equal to 1, then only one variable is required to explain the state of the system. Again, if I am having f is equal to 2, that is, if the system is bivariant, that is, above these three variables, that is temperature, pressure, and concentration, I will be needing two variables, that is either temperature, pressure, then concentration can be explained on its own. Either I can take pressure and concentration if I explain, then temperature of the system will be already clear. Now suppose if I am having f is equal to 3, that is the system is said to be trivariant, then at that particular time I need to explain all the three variables. I need to explain what is the temperature of the system at that particular time, what is the pressure of the system, and as well as what is the concentration of the substance. So this is how things go in f is equal to c minus p plus 2. Now consider a one component system. Consider a one component system, like for example, as I already said, water. So already water, it is existing as a one component, and suppose water is existing in its minimum state. Suppose p equals to 1. P equals to 1 is minimum state because the system should be in any state. So it should be equal to p is equal to 1, the minimum phases. So according to Gibbs phase rule, if component is equal to 1 and its number of phases equal to 1, then f equals to 2. That is, at that particular time I will be required two variables. So then again, if I take the example of water, if component is 1, then if water is existing in two different phases simultaneously, like suppose there is an equilibrium between solid and liquid phase, then at that particular time the degrees of freedom will be 1. That is, one variable will be required. And suppose again, if water is existing in three different phases, like there is a critical point. There is a critical point when all the three phases are in equilibrium with each other, then at that particular time no variable is required to explain the state of the system. So this is the significance of Gibbs phase rule. Now in this particular system, water, we all know water, it can exist in three different phases: solid, liquid, and vapor, with these possible equilibrium. That is, there can be an equilibrium between liquid and vapor, there can be an equilibrium between solid and vapor, and there can be an equilibrium between solid and liquid. So each equilibrium involves two different phases. Suppose this first equilibrium, if I consider liquid and vapor, then these two phases are required. So here component is 1, but phases are 2. Again here component is 1 in second equilibrium, component is 1, but two phases are required, that is solid and vapor. And again in third, the component is again only 1, but two phases are required, that is solid and liquid. So in each of these equilibrium, two phases are required. So this is the phase diagram of water system. It is clearly seen that this phase diagram, it consists of three different regions. We can see our first region, that is COB, second region is BOA, and third region is AOC. So these three regions, on the basis of temperature and pressure, they have different states. Like the region COB, this is showing me complete solid state because the temperature is below 0 degrees Celsius, and we all know that below 0 degrees Celsius water exists in solid state. Then as we increase the temperature, the solid starts to liquefy, and then we will be reaching the stage COA, where solid is getting converted into liquid. And in that particular case, solid and liquid, they are in equilibrium with each other. Similarly, if again I increase the temperature, then all the liquid will get converted into vapor. That is the region that I am talking about, AOB, the vapor state. Here liquid and vapor, they are in equilibrium. So in all these three regions, that is COB, that is solid, COA, that is liquid, and AOB, which is vapor, here according to the Gibbs phase rule, that is f is equal to c minus p plus 2, here degrees of freedom can be calculated as 2 because the number of component is 1 and the number of phases is only 1. That is, either it is solid in one region or liquid in another region, and it may be vapor in the third region. So this is how we can calculate the degrees of freedom. So these and again in this particular phase diagram of water, we can see three different curves: curve OA, curve OB, and curve OC. And in these particular curves, the degrees of freedom comes out to be 1, and that is the system is univariant. And this is the mathematical explanation of all these regions and curves. So this is the Clapeyron equation with the help of which we can calculate the change in pressure with respect to temperature. And in this particular phase diagram of water, we will be having one triple point that is invariant, where the degrees of freedom comes out to be 0. That is F is equal to 0. That is no variable is required to explain the system, and this point is known as triple point. Thank you so much.